Welcome everyone. Thank you for joining. Today, we'll explore an advanced technique used in credit scoring, reject inference. Reject inferencing methods are critical for improving predictive accuracy and making better lending decisions. We will look into how AI and synthetic data methods can inform and enhance these techniques. My name is Pat Bhattacharya, and joining me today are my colleagues Krishna Mehta, Reshmi Bhaskar, and Shikha Agarwal. A common problem in credit scoring is that we can observe only the behavior of applicants who have received loans. Rejected applicants have not received a loan at all from our lender, and so they cannot default on any such loan. The dependent variable is therefore unknown for rejected applicants, and so models can only be trained on accepted applicants, which introduces bias. To remove this bias, we need to estimate how rejected applicants would have performed, and that is the goal of reject inferencing. One technique for inferring the behavior of rejected population is bureau augmentation, which involves enriching your internal data with bureau data. Why do this? Well, because rejected applicants may have taken loans from other lenders and they may have defaults elsewhere. And we can use that data to estimate the dependent variable for the rejected applicants. Combining our internal data for the accepted population with external data for the rejected population makes our dataset more complete and reduces bias. However, bureau data may not be available for all rejected applicants as they may not have obtained loans from other lenders during the same observation period. In fact, in most cases, using credit bureau information alone will not be sufficient to tag the entire through the door population. That is why we need other, more analytical methods for reject inference. One approach of reject inference is a simple proportional assignment. This method involves random partitioning of rejects into good and bad accounts. The assumption is that the default rate is higher in the rejected sample than in the accepted sample. Usually, we assume that the rejected sample has a bad rate that is 2 to 5 times higher than in the accepted population. This method is very simple and does not require us to build a model on the funded applicants. Another approach involves building a model on the funded population and using it to score the rejected applicants. We assume that the model estimates the probability of default within the funded population, with higher scores from the model indicating a greater likelihood of default. Once scores are assigned to the rejected population, various techniques can be applied to infer the default status for the rejected applicants. And that is what we will discuss next. In the hard cutoff method, a cutoff score is used to classify rejects as good or bad. Those with scores higher than the cutoff are classified as defaults or bads, and those with scores lower than the cutoff are classified as non-defaults or goods. Usually, the cutoff score is chosen to make sure that the proportion of defaults in the rejected population is higher than in the funded population. Another method of reject inference is fuzzy augmentation. In this method, each rejected applicant is transformed into two separate observations. One observation is given a bad status and a weight equal to the predicted probability of being bad. The other observation is given a good status and a weight equal to the predicted probability of being good. The new duplicated and weighted observations for the rejected applicants are combined with the data on the accepted applicants to create a new augmented dataset. A new final model is then trained on this augmented dataset. The third method for reject inference is called parceling. First, we take the rejected applicants and sort them by their scores from the funded-only model. Then, we divide them into equal-sized bins as shown. In this chart, the bins at the top have higher scores, while bins towards the bottom have lower scores. We then assign a default rate to each bin. Higher score bins get higher default rates than lower score bins. We do this in a way that ensures that the overall default rate in the rejected population is higher than in the funded population. Finally, we randomly assign some observations in each bin as bad based on the default rate assumed for that bin. So all of these reject inferencing methods are powerful tools for enhancing credit scoring models. When we have bureau data available, we can use that, but a lot of the time we also have to use some of these other analytical approaches we discussed, as bureau data is not available for the entire rejected population. From our experience, we have found bureau augmentation combined with data parceling to be the most effective of all of these methods. So in our experiments, we have taken this to be the baseline, as we will see later in this presentation. We next delve into the topic of synthetic data, which is artificially generated information that mimics real-world data. It is generated using mathematical algorithms, statistical processes, and artificial intelligence methods. One of the characteristics of a good synthetic dataset is that it should not contain any direct or inferable private information from the real dataset. Synthetic data generation methods have existed for years. However, recent advances in AI, particularly in the areas of large language models and computer vision models, has significantly improved the quality and feasibility of generating synthetic data. One of the models we experimented with creates synthetic tabular data using a large language model. To allow a large language model to work with tabular data, we first have to convert the tabular data to a textual format. For instance, suppose the tabular data contains a value of 3 for the variable number of inquiries in the past 6 months. The way to convert this to text is by using the words number of inquiries in the past 6 months is 3. This text is then fed into large language models, which can then spit out new synthetic textual data, which once again is converted back to tabular format to create new synthetic samples. Another type of model that we experimented with is diffusion models. These models originated in the field of computer vision and are excellent at new image generation. Diffusion models progressively add noise to training data until all features are completely random. The model then learns to reverse the process and create new synthetic samples from noise. We next ask an important question. Can synthetic data techniques help with reject inference? Now, synthetic data is only valuable if it produces results that are comparable to real data. This was the motivation behind the experiments that we conducted, and my colleague Reshmi will walk you through some of those experiments later in this presentation. While working with synthetic data, there are also some critical points to watch out for. One is that it must not be too similar to real data, as that could violate privacy laws. At the same time, the distributions in the synthetic data should resemble those in real data to maintain analytical validity. My colleague Shikha will now explain these considerations in detail and also share how we address them during our experiments.
Thank you, Pat. Good morning, everyone. My name is Dr. Shikha Agrawal. Today, I will talk about the quality checks we use to make synthetic data more reliable. When we create synthetic data, two big challenges come up: keeping the data similar to the real data and protecting the privacy. To solve these issues, we use two key measures: distribution fidelity and DCR-based privacy filtering. Distribution fidelity checks if the synthetic data looks statistically similar to the real data, and DCR-based privacy filtering makes sure that synthetic records are not too close to the real data, so privacy is safe. On the next slides, I will explain each measure in detail. Distribution fidelity tells us how closely synthetic data matches the real data. To check this, we look at the key statistics for each variable: mean, median, quantiles like 25th and 75th percentile, minimum and maximum values. If these numbers are very similar to the real and synthetic data sets, it means synthetic data has good fidelity. This slide explains how we check privacy using DCR, which stands for distance to closest record. For synthetic record, we measure how far it is from the nearest real record. If the distance is 0, that means the synthetic record is identical to a real one, which is privacy risk. We want this distance to be a bigger number. We also look at the median DCR, which is the middle value when we list distances for all records in the data. A high median DCR means most synthetic records are far from real records, so privacy is well protected for the dataset. We need to look at both measures, as overall dataset might be good with privacy, but some records might violate privacy. Looking at both measures ensures privacy is maintained, both the record and the dataset label. This slide explains how we balance two important measures: DCR privacy, which is used to keep the synthetic records far enough from the real ones, and distribution fidelity, which is making sure synthetic data looks like real data. If we push privacy too far with very high DCR, the synthetic data may lose similarity to real data and model can become weaker. So we need a balance. Our approach uses a data-driven DCR threshold. We check distribution fidelity to keep the data useful and at the same time apply DCR filtering to protect privacy. This way the synthetic data is both safe and practical for analysis. This slide explains different challenges of the experiment. Segment level strategy. Our dataset had three very different segments: funded, non-funded bureau, non-funded non-bureau. Each segment behaved very differently. A single strategy of synthetic data generation for all the segments at once was giving poor results. However, once we broke the data up into the segments and generated synthetic records at the segment level, the performance improved significantly. Initial pitfall. At the first attempt of synthetic data generation, we generated synthetic data that had statistical differences and privacy risk. But model built using that data set was showing good results. This was primarily driven by a lot of synthetic records being duplicates of the real records. Therefore, quality and fidelity tests are needed before modeling exercise. Statistical alignment. We also face the challenge of matching the mean, median distribution of the synthetic data with actual data. Only after multifold generation of a large number of synthetic records and filtering, the statistical property stabilized and aligned with the actual population. Privacy risk. When we generated one-to-one synthetic data, some records were almost identical to the actual population. This creates privacy concern that actual identity might leak unless proper DCR tests are performed. Dynamic privacy threshold. There is no standard DCR metric for how close a synthetic record can be to a real record and will vary from case to case. In our experiment, we use the median DCR of actual data as dynamic data-driven threshold. Bias risk. We generated multifold synthetic data to solve the issue of privacy and statistics. But if synthetic data outnumber actual data, the model becomes biased towards synthetic patterns. To prevent this, we kept only an equal number of synthetic records as the original non-funded bureau population. Challenge of utility privacy trade-off is very real. As we know, cleaner the data, the safer it is. But too much cleaning removes realistic examples needed for accurate reject inferencing. Reaching a balance was a constant trade-off. This slide shows the result of our distribution fidelity test. This slide shows how close the synthetic data is to the real data by comparing the mean of 5 variables across 3 sources: actual data, LLM generated data, diffusion model generated data. LLM data shows big differences from the actual values. For example, for variable x1, the actual mean is about 65.8, but LLM gives 57.8. In contrast, diffusion model is much closer at 66.0. The same patterns hold for other variables. The key takeaway from this experiment is diffusion model values are very close to the actual data while LLM deviates more. This slide shows the result of our DCR-based privacy filtering test. We compared three models: base model, LLM model and diffusion model. Base is actual versus actual model. This gives us a reference DCR threshold. Median DCR before means the median distance for all synthetic records. Median DCR after means the median distance after removing records that were too close to the real ones. For the base model, the median DCR stays at 2.28 because we don't remove any real record. For LLM model, the median DCR improves from 0.998 to 2.37 after filtering, which means privacy got much better. For the diffusion model, the median DCR stays around 2.26 before and after, so no need of filtering. The key takeaway from this experiment is diffusion model already preserves privacy well, while LLM model needs filtering to meet privacy standards. Next, my colleague Reshmi will walk you through the experiment details and results.
Thank you, Shikha, for handing over the presentation. I will now walk you through some of the experiments we conducted to compare and analyze model performance under two scenarios, using actual data and using synthetic data. First, let's talk about the data. Our actual modeling dataset consisted of two segments: funded population of customers who were approved and booked in the past, non-funded population of customers who were rejected previously. As we know, building a model solely on the accepted customers introduces bias and ignores valuable insights from rejected applicants. To address this, we performed reject inference. As Pat discussed earlier, reject inference helps lenders and financial institutions estimate how rejected or non-booked applicants might have performed had they been accepted. By incorporating this process, we gain a more complete view of the applicant pool, leading to better informed underwriting decisions. Since rejects were never booked, we lacked outcome data for them. To overcome this, we applied a two-way approach to assign dependent variable values. For non-funded customers with bureau data, we augmented the dependent variable using bureau information. For non-funded customers without bureau data, we used a data parceling technique to assign values. In addition, we generated synthetic data and used it for reject inference. Our experiments involved training on actual non-funded bureau data and generating synthetic samples using both LLM-based approaches and diffusion models. In the following slides, I will walk you through each experiment using synthetic data and share the results we observed. We conducted 4 experiments where actual data was either augmented with or replaced by synthetically generated data. The goal was to understand how these different approaches to reject inference, bureau augmentation, data parceling, and synthetic data work together, and if there was a scenario that led to superior results. Let me talk about experiment 1. Now, what was the goal here? We wanted to replace the dependent variable for the non-funded non-bureau segment with a synthetic version. And how did we generate it? We used two approaches, an LLM-based method and a diffusion model, both trained on the non-funded bureau data. What did the model look like? We kept the entire actual dataset intact. For the non-funded non-bureau customers, we swapped out the actual dependent variable with the synthetic one. Let's take a quick look on how the first experiment performed. For the traditional data parceling model, the AUC was 0.723 on training and 0.719 on validation, with the holdout test matching validation at 0.719. For the synthetic LLM model, both training and validation came in at 0.739, while the holdout sample scored at 0.707. For the synthetic diffusion model, training AUC was 0.742 and validation AUC came in at 0.760, while the holdout sample scored 0.705. Now, what does this tell us? The synthetic models are feasible and achieve good performance on all samples. They outperform the traditional data parceling on training and validation, but the traditional model edges ahead on the holdout test, showing better generalization. In experiment 2, the non-funded bureau data was replaced with synthetic non-funded bureau data. Here, the model sample contained the actual funded population, the actual non-funded non-bureau data, and synthetically generated non-funded bureau data. Now, let's see how the second experiment turned out. Traditional model, train AUC 0.723, validation 0.719, holdout 0.719. LLM model, train 0.729, validation 0.716, holdout 0.713. Diffusion model, train 0.716, validation 0.707, holdout 0.717. Now, what stands out here? All three models are in the same range, very close overall. The LLM model leads on training performance, while the diffusion model is closest to the traditional model on holdout, showing strong generalization. In experiment 3, the original modeling data was stacked with synthetic non-funded bureau data. Here, the model sample contained the funded, bureau augmented non-funded, non-funded with data parceling, and a synthetically generated sample of non-funded bureau data. Let's check the numbers for this experiment. Traditional model, train 0.723, validation 0.719, holdout 0.719, LLM model train 0.728, validation 0.718, holdout 0.718, diffusion model train 0.719, validation 0.715, holdout 0.720. What do we see here? All results are very close, again in the same ballpark. The LLM model leads on training while the diffusion model slightly beats the traditional model on holdout, showing strong generalization. In experiment 4, the synthetic non-funded bureau data was added with the sample after removing the non-funded non-bureau data. Here, the model sample contained the actual funded population, actual non-funded bureau population, and the synthetically generated non-funded bureau data. Let's look at how the final experiment performed. Traditional model, train AUC 0.723, validation 0.719, holdout 0.719. LLM model, train 0.741, validation 0.734, holdout 0.713. Diffusion model, train 0.728, validation 0.729, holdout 0.713. Now what stands out? All results are in the same ballpark, showing strong consistency. Both synthetic models outperform the traditional model on training and validation, with the LLM model leading. On the holdout set, the traditional model performs a little better than both the synthetic models, indicating strong generalization. I will now hand over the presentation to Krishna for his insights and takeaways. Thank you.
Thank you, Reshmi, for taking us through the results. I would now like to spend a little bit of time analyzing the results for you. The first thing is that uh, our reject inference approach is broadly defined into two categories. The first category, we are using the rejects for whom the performance is known through the bureau to create synthetic rejects, which we then use in our model development. And the second approach is that we actually impute the performance of the existing rejects using traditional methods like data parcelling or synthetic methods using large language models or diffusion models. Let us now talk about insights from the synthetic reject generation process. So we have seen these results from the different experiments we conducted, and one thing that stands out is across all the results when we compare the diffusion model and the large language model, what we see is that in all the experiments uh, the diffusion model outperforms the large language model. Why is that? So as Pat had shown you, diffusion models iteratively add noise during the sampling process, enabling gradual refinement of the data. Now, because they are doing that, they are introducing a controlled randomness into the sample, uh, which adds greater robustness to the process as compared to the large language model approach. And this leads to better generalization, and therefore we get less overfitting and therefore superior model performance on holdout samples. Let us now talk about the insights we obtained from our experiments where we did not generate new synthetic rejects but rather imputed the performance on the rejects that were already available to us. In this case, we see that on the holdout sample, data parceling does much better than the AI methods which we applied. Why is that? So, imputing the performance of a rejected applicant, or any applicant for that matter, is a conditional process. It depends on the other attributes that are available for that applicant. Uh, that is the whole premise of credit risk modeling. Now, in data parceling, we are using a model which was built on the funded population to score the rejected population, and using that as the basis to impute rejects. Because of that, data parceling approach captures the conditionality needed to make this imputation, and therefore stands out as opposed to the other approaches. Now, another thing we observe is large language model does slightly better here than diffusion model, and uh, maybe a reason for that is how large language model handles the prompts. I'm showing you here a typical prompt you would feed in this case. Maybe it would be longer, but something like number of inquiries in the past 6 months is 3, FICO is 650, time in business is 8 years, and the account has defaulted. Because large language model would sequentially process this prompt, it would get a better sense of conditionality and do a better job. And another thing which we cannot discount is large language models always leverage domain knowledge. And because of that, we feel large language models doing a little better job than diffusion models in this case. Let us now talk about which approach gives us the best result. So we did 4 different experiments which my colleagues shared with you. In some we took portions of the sample out, and in others we kept everything together and added the rejected uh, sample which was generated using AI. Now, what we see is whether we look at large language models or diffusion models, experiment 3 does better. Not only that, but experiment 3 actually, if you look at the results for diffusion model, it is the best result we have for the holdout sample across all uh, the different experiments we did. So it's by a small amount, but still it is the best. So why is experiment 3 doing so much better, and what is experiment 3? So experiment 3 is when we combine the bureau augmentation, the data parceling, and then we add to it synthetic data generated using the AI process, whether it be large language model or diffusion model. So we are not taking anything out. This is the process where we are adding more to the sample. Why does this do the best? First, bureau augmentation fills a data gap for us. We have this population which was not booked, and for them we do not observe their performance within our portfolio. So we go to the bureau, we look for a corresponding period of time, and we look for a loan product which is similar to our loan product, and we get the performance from there, and using that we infer what the performance would have been for our loan. It's a very useful process. Now, What does data parceling do? What data parceling is doing is it's leveraging a, a model which was built on funded population within our own sample. So it is capturing the patterns and the dynamics which are unique to us within our sample, and using that, it is leveraging that to generate our best guess of how the non-booked population would have performed. So it's doing something very different from what bureau augmentation does. One is looking externally and the other is looking and finding internal patterns. And then on top of that, the AI generated synthetic reject data is adding more robustness to the model by giving greater voice and representation to underrepresented groups and to edge cases. And because of all of this, the combination of all these three methods gives us a very strong team for our reject inference, and together they come out strongest in our experiments. A fair question to ask at this point is that we have established through our experiments that synthetic rejects do add value to the sample, but it's not by a very big amount, so why bother? I'll give you 3 reasons why organizations should seriously consider this process. The first one is lowering the costs. Because bureau data is very expensive, if you could reduce the dependence on bureau data, uh, then you will lower the expenditure, and over time this could add up. The next thing is superior performance. Yes, uh, the gains might not be very large, but they are there. And not only that, because your reject population is drawn in 3 different ways and they focus on different aspects, uh, your overall sample is better built and will be more robust to the test of time and external shocks. And the third reason is regulatory compliance. Synthetic rejects help increase representation of marginalized and underrepresented groups and will lead to better compliance. So what is next for us in our AI experiments? We are working with computer vision AI to address the multi-level classification task, where we can take an asset and use computer vision AI to classify into one of multiple buckets. So it could be like an equipment returned, is it in good condition, fair condition, poor condition, something along those lines. Another area where we are doing a lot of work is synthetic data. Uh, just like we presented applications of synthetic data for reject inferencing in this session, we would be bringing you results of our experiments on applying it to other business cases, uh, like customer churn prediction, fraud detection and prevention, and donor acquisition in the coming months. And finally, we are taking all the learning we have acquired in computer vision AI, large language model, and synthetic data generation to focus on a problem which a lot of small lenders face. That is, they have a lot of uh, non-tabular data and very sparse data. And we hope to bring something on that to you again in 2026. I would now like to acknowledge my colleague Jisha Augustine, who did not present today but has done substantial work on this project. Thank you so much for making the time to attend this session. I hope you found the contents to be useful. Now we will open up for questions and answers.